Imagine language as this incredible, really intricate puzzle. We use it every single day, right? But have you ever really stopped to think about its smallest, most basic pieces? And what if we told you that the way we break down words for meaning, well, it isn't universal, especially not when you compare how our human brains do it versus how, say, a cutting edge AI machine tackles it. So today, we're taking a deep dive into two really powerful concepts that help us unlock this linguistic puzzle. First, the morpheme, which is, cornerstone of classical linguistics, and second, the token, the sort of digital currency of today's large language models. Our mission for you today is to help you get crystal clear on what each term means, how they fundamentally differ, and crucially, why this distinction matters for anyone trying to grasp how AI processes and, well, seems to understand language.
Yeah, it's a truly fascinating journey. We're going from the inherent meaningful building blocks of human communication,
Yeah.
all the way to these purely computational units that power the most advanced AI systems we have right now. And what's so intriguing, I think, is how these two concepts, they seem so different, but they actually share some surprising functional parallels. Yet, fundamentally, they diverge in their purpose and their very construction. By the end of this deep dive, you'll definitely have a much clearer picture of the sort of intricate machinery behind both our own minds and artificial intelligence, and maybe, just maybe, a new way to look at language itself.
Okay, let's start with the human side then. The first piece of this puzzle, the morpheme. It might sound a bit technical, maybe something from an old textbook, but once you get it, it's actually incredibly intuitive. It's really about how we naturally find meaning in words.
Precisely. In classical linguistics, a morpheme is consistently defined as the minimal meaningful unit in a language. Think of it like the smallest possible piece, an indivisible piece of a word that still carries its own distinct meaning. Or maybe a specific grammatical function is like an elementary unit.
So it's not just about a single sound, is it? Because a sound on its own, like s or eat, doesn't inherently mean something specific in most contexts. The morpheme has to carry that semantic weight, you could say.
Absolutely, that's the critical part. It's what linguists call a two-sided unit,
Mm.
meaning it has both a signifier, that's its physical form, the sound or the written letters, and it has a signified, which is its semantic content, its meaning.
Mm.
And those two sides, they're totally inseparable in a morpheme.
Okay, that makes perfect sense. Could you maybe walk us through a classic example? How does this actually break down in a common word?
Certainly. Let's take a word like unbelievable. Pretty common word. If we apply what's called morphological analysis, we can break it down into three distinct morphemes. You have un, believe, and able. And each of those parts, each morpheme, it contributes its own layer of meaning. Un gives you negation, right? Flips the meaning. Believe is the core action, the root. And unable indicates capability or possibility. So unbelievable literally means not capable of being believed. Each piece adds up.
Ah, I see. It's like taking apart a Lego model to see the individual bricks and understanding what each brick actually contributes to the final thing. So morphemes are truly foundational to how we process and understand words. We do it all the time, probably without even thinking.
Exactly. Morphemes are a fundamental element of our language system. They sit at a specific level of analysis,
Yeah.
smaller than whole words, but they're built from phonemes, which are just the smallest sound units, without inherent meaning themselves. For linguists, identifying these morphemes is absolutely crucial for achieving the most, let's say, efficient and systematic description of any language's structure. But, and this is key for our discussion, if meaning is so central to these human linguistic units,
Yeah.
how does this translate when we pivot to artificial intelligence? Doesn't AI even, care about meaning in the same way we do?
Yeah, that really is the million-dollar question, isn't it? Because when large language models, LLMs, process text, they aren't actually looking for our morphemes, these meaning-based units. They're encountering something quite different, tokens. And this is where things get really interesting and maybe a bit counterintuitive.
Indeed. Tokens are the raw fundamental units that LLMs use to break down text. They could be whole words sometimes, or single characters, or more often now, combinations of partial words and punctuation. It's the very first step, the foundational move an LLM makes when it sees text, especially during its training.
Okay, so a token is less about inherent meaning, like a morpheme, and more about being the raw, like the digital byte that the AI can actually work with, the basic unit it processes.
Precisely. That's a good way to put it. The LLM then analyzes the statistical relationships and sometimes semantic patterns between these tokens. Things like how often they appear together, in what order, or in similar contexts across vast amounts of text. After all this intensive training, it leverages these learned patterns and relationships to generate new sequences of output tokens. It's fundamentally about prediction and pattern recognition at that level.
How does an LLM actually do that initial translation, taking a normal human sentence and chopping it up into these digital units, these tokens?
Right. Let's take a simple sentence. I heard a dog bark loudly at a cat. A very common method, maybe an older one, is word tokenization. That would simply split it like this. I heard a dog bark loudly at a cat. Each word becomes one token. Pretty straightforward.
But I feel like I've heard that's not the only way, and maybe not even the main way modern LLMs do it. There are more granular methods.
Yeah, absolutely right to pick up on that. Simple word tokenization has its limits. Beyond that, we also have character tokenization, which, well, it does what it says. Splits text into individual characters, A, B, C, space, etc. But the most established, the most widely used approach for today's big LLMs is subword tokenization. This is where words are broken down into smaller, meaningful-ish pieces like partial words or common character sequences. Things like Byte Pair Encoding, BPE, that's a popular type of subword tokenization. OpenAI's GPT models use something like this.
Okay, hold on. Why would they choose to break words into subwords, it feels? Less intuitive than just using whole words, doesn't it? What's the advantage?
Yeah, it might seem less direct, but it's really about striking a crucial balance, a balance between efficiency and capability. So with smaller tokens, like character or subword tokens, the model gains a lot of flexibility. It can handle a much wider range of inputs. Think about words it's never seen during training, or typos, or really complex compound words like in German or Finnish. A really big benefit is also that it reduces the total vocabulary size the model needs to store, which saves memory. But there's always a trade-off. The downside is that any given piece of text gets broken into more individual tokens, and more tokens generally means more computation is needed for processing. Plus, if there's a fixed limit on how many tokens the model can handle at once, which there usually is, then using smaller tokens means the maximum amount of text it can process is shorter.
Okay, I see the trade-off there. And what if they went the other way with larger whole word tokens? What are the pros and cons then?
Right, so for larger tokens, like with that classic word tokenization, you naturally get fewer tokens for the same amount of text. This means, generally, less computation is needed, and with the same token limit, the model can handle a larger chunk of input or output text at once. However, this approach usually leads to a much larger vocabulary size. You need to store every single word variation. That takes up a lot more memory. And critically, it really limits the model's ability to generalize. It struggles with words it hasn't seen before, unknown words, new slang, typos, creative spellings. It just sees an out-of-vocabulary item.
Wow, so it really sounds like this isn't just some minor technical detail. The way you choose to tokenize text has these huge real-world impacts on the LM's performance, its cost to train, its cost to run. It's like a fundamental design choice.
Oh, absolutely foundational. There's research that vividly shows how the tokenizer choice can drastically change a model's performance and its training costs. For instance, if you take a tokenizer that was built just for English, a monolingual one, and try to use it on data with lots of languages, it can lead to significantly higher fertility. That's the term for how many tokens, on average, it takes to represent a single word. And this higher fertility can result in up to, say, 68% more computational cost during training, which in turn can potentially hinder the model's ability to learn those crucial long-range dependencies, understanding connections across long sentences or paragraphs. It really shows that not all tokens are created equal, even if they look like just, arbitrary bits of data to us. The choice matters.
Okay, now let's bring these two concepts right next to each other. This is where it hopefully all clicks for you, our listener. We've seen how morphemes are these meaningful building blocks for humans, and tokens are the computational units for AI. So what happens when we actually compare them? The meaning-making morpheme versus the computational token, are they similar, or is there like a deep divide?
Yeah, connecting it all is key. And there are actually some fascinating parallels, especially if we zoom in on that subword tokenization method. That's where the two concepts seem to get closest, functionally speaking.
Okay, tell us more. What are those similarities, the things that might make us think, oh, maybe AI is doing something like morphemes?
Well, first, both morphemes and tokens act as fundamental units of decomposition. Right. Morphemes are the smallest units carrying meaning for linguistic analysis, how we break down language to understand it. Tokens are the fundamental units LLMs break text into for processing how they break down language to compute it. So a basic unit idea. Second, they both share this ability to decompose complex units. Linguistics breaks down big words like unbelievable into morphemes, unbelievable, to get at the layers of meaning. Subword tokenization does something functionally similar, breaking words into smaller bits, maybe like unbelieve able, which helps the LLM handle unknown words, typos, complex structures. It's a functional parallel, even if the reason is different. And third, both approaches help in handling unknown or new units. Just like understanding morphemes, like knowing what softness or re means, helps us guess the meaning of a brand new word we encounter. Subword tokenizers can process words they've never seen by just combining smaller known subwords from their existing vocabulary. It's a coping mechanism for novelty.
That is actually quite a bit of overlap in function. It almost makes you think that AI maybe accidentally stumbled upon a similar kind of linguistic granularity that humans use. But I have a feeling there must be some really crucial differences underneath that functional similarity, maybe even kind of philosophical differences.
That is exactly the core of it. If they function so similarly in some ways, why do we even need two different terms? The absolute key lies in their basis of definition, how they come into being. Morphemes are primarily meaning-based. Their whole identity, their identification, is completely rooted in their semantic function. What do they mean in the context of human communication? They are, you could say, natural organic units of human language, something we discover through linguistic analysis of how language works.
Okay, so morphemes are discovered within language by looking at human use, but
Yeah.
tokens, are they discovered in the same way or are they engineered, constructed?
That's an excellent way to frame it. Tokens, especially subword tokens, are primarily statistically or algorithmically defined. Their creation, how they're decided upon, often depends purely on the frequency of character strings in the massive amounts of training data. Like with byte pair encoding, it just merges the most frequent pairs of characters or sequences. Now, these tokens might sometimes correlate with morphemes. A common prefix like "un" might end up being a token because it appears frequently. But the tokens themselves are not inherently meaning-carrying in the way a morpheme is. They are essentially artificial constructs, engineered specifically for computational efficiency and processing. The LLM analyzes the semantic relationships between these tokens. Sure, it learns patterns, but the tokens themselves, they're just the raw data the model works with, not inherently meaningful linguistic units like morphemes are to us.
Right. So it's the difference between a naturally occurring unit that we humans seem to use almost intuitively for meaning and a computationally engineered unit designed purely for efficient pattern finding and prediction. That feels like a really profound distinction. It really changes how we think about whether an AI truly understands language in the human sense.
Precisely. And this isn't just theoretical. Research backs this up. It indicates that while those intrinsic tokenizer metrics, like fertility, remember how many tokens a word needs, while they can be important, there's actually no clear, consistent correlation across all types of tasks in different languages between metrics like low fertility and the actual downstream performance of the LLM, how well it actually performs a task. So having low fertility using fewer tokens per word, it might be a necessary condition for good performance in some cases, but it's definitely not sufficient on its own. For example, for English, research suggests that once you reach a certain level of low fertility, maybe around the 33,000 token vocabulary size, just adding more tokens to the vocabulary might not actually improve performance much, if at all. And it could even increase computational costs, especially if those extra tokens don't actually capture deeper, more meaningful morphological segmentations, the kind of breakdowns that align more with human morphemes. So it's not just about smaller pieces. It's about whether those pieces capture something useful. And AI's useful isn't always our meaningful.
Wow, what an absolutely eye-opening journey we've taken today. Really, from you could say, the soul of human language, the morpheme,
Hmm.
all the way to the digital nuts and bolts of AI, the token. We've seen how classical linguistics carefully, meticulously breaks down words based on inherent meaning, while modern AI approaches text through this computational lens, often creating units that are much more about statistics and algorithms than about semantics in the human sense.
Yeah, and understanding this distinction is, I think, vital for anyone interested in language or AI. It highlights not only the elegance and the sort of inherent structure of human language, but also the incredibly ingenious engineering that goes into building these large language models.
Yeah.
It really shows us that while AI can mimic, process, and generate language with astonishing ability, its fundamental units of understanding, if you can call it that, are constructed really quite differently from our own. It's like a mirror, maybe, but a distorted one in some ways.
So for you, our curious listener, maybe the next time you interact with an AI chatbot, or even just read a sentence, take a moment to consider those invisible layers underneath the surface, the natural, meaningful morphemes that shape our human world of communication, and the calculated statistical tokens that shape the digital one processing that communication. They're both pieces of this grand linguistic puzzle, but they approach it with fundamentally different logic.
And perhaps this leaves you with a final thought to mull over. As AI continues its rapid evolution, as the models become even more sophisticated. Will its tokens ever truly align more closely with our morphemes? Will they start to capture meaning in a way that resonates more with human intuition? Or will they always remain a computationally efficient, powerful, yet ultimately distinct reflection of human meaning, forever defined by algorithms rather than inherent significance? Something to think about.